sine x, you have sine ugly. What is the derivative of sine ugly?
Cosine ugly. The derivative.
Cosine, same old ugly.
And the derivative of that ugly.
And then derivative of the ugly. Now,
Which is
if the...
fun.
I'm sorry? Yes. If the derivative was only going to be one term, then I wouldn't need any more parentheses. I could use a dot if I wanted to make it clear to my eyes that that's multiplication. But the product rule is, the derivative of the ugly is going to take the product rule, and that whole product rule has to be multiplied by the cosine of xy. So I'm either going to use brackets around the expression I get when I use the product rule or another set of parentheses. But I need to understand it's cosine times this whole thing, not just cosine times the first term. I'm working on the derivative of x times y by the product rule. The first term is x. The derivative of the second term is what? Y prime. Or 1y prime, you just don't have to write the 1. That's the first term of the product rule. And then the second term is y times the derivative of the first. What's the derivative of the x? 1, and you don't have to write it. If you didn't have those brackets or another set of parentheses here, then the way that you would solve for y prime would be completely different. If that y prime, if that cosine was only multiplied by the first term, you'd get a completely different answer. So my person in Harriman who asked me that, did you have these parentheses or brackets?
No.
Do you see what a difference that would make now?
Yes.
That I would have to distribute the cosine and then subtract this term that had a y prime in it, and then factor and then divide. You think you could finish it from there?
I can get close.
Let me do one more step to make sure that you get close enough. All right, xy prime times cosine xy is the first term on the right-hand side, and then the second term on the right-hand side is y cosine xy. And now it's just a matter of, like all the other problems, get the terms with a y prime on one side, the terms without a y prime on the other. So I would subtract this guy, then factor out a y prime, and then divide by what was left inside parentheses.
All right, that's what I thought I'd do.
Okay, all right. And then, so I'm going to put a dot, 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 a couple more steps there, and let's look at 19. Oh, yes.
What if it is again x divided by y? Would you have to put the whole quotient rule?
Well, let me, if you said if this were x divided by y and I was using the quotient rule, would I still have to have these brackets? I would still put those brackets, but they would be, the answer to your question is definitely yes. Yeah, you would still need those brackets, even if you would use the quotient rule instead of the product rule there. All right, number 19, x squared minus 3 natural log of y plus y squared equals 10. What's the derivative of the first term? 2x. Derivative of the second term, do I need the product rule with that since it's negative 3 times something? No, because that's a constant times a function. I can just keep up with the constant and differentiate the function. The derivative of natural log of y is what? 1 over y times y prime. That's the derivative of the second term. What's the derivative of the third term? 2y y prime. And the derivative of the right-hand side? 0. All right, my person in Harriman, did you get that line?
Okay, yeah, I didn't get the y prime right there.
In
with
which
the natural
terms?
the natural log one, with the natural log one.
Oh, okay, you just had 3 times 1 over y, you didn't have y prime?
Yeah, I just had negative 3 over y.
And that would change everything. Now
Yeah.
you have two terms with a y prime in it. Get that by itself, then factor, then divide. All right, I really hated that I only had one example of a logarithmic differentiation before you tackle this homework. Those problems were 71 to 81. Does anybody need to see one of those?
Yes.
They got really ugly.
Okay, I'm going to do 79 because that's the one I think would be the most difficult. If I had just, let's say, 2 to the x plus 1, what rule would I use? What differentiation rule would I use? That would be the derivative of just a constant to an exponent. Is that where I bring the exponent out front and subtract 1 from the exponent? It's not. That would be the derivative of a to the ugly is a to the same old ugly times the derivative of the ugly. If the base was a constant, I'd use that rule. If the exponent was a constant, say that was just x minus 2 cubed, then I'd use the power rule. I'd bring the 3 out front, same old x minus 2, subtract 1 from the exponent, and so on. But this is neither of those. I have x's in the base and x's in the exponents. That's really an ugly to the ugly. So, in logarithmic differentiation, I take the log of both sides, which is a legal thing to do, but ordinarily not something you would think to do, unless the directions said use logarithmic differentiation. So far, so good? Waiting on a yes from Harriman. Yes. Okay. And why introduce logs into something that didn't have logs to begin with? What is the purpose of that? So that you can make this an expression that's easier to differentiate using the properties of logs, breaking logs of products apart as the sum of logs, or logs of quotients as the difference of logs, or logs of something to a power to bring the power out front. Can I take the derivative of the right-hand side now by just saying the derivative of x plus 1 is just 1, the derivative of natural log of x minus 2 is just 1 over x minus 2? Would that work?
No. It's x plus.
It's a product.
That's a product. It's going to take the product rule. On the left-hand side, the derivative of natural log of y is 1 over y times y prime.
Is this horrible because you have an X and
Yes, if this were just, for example, 5 times natural log, then I could just keep up with the 5 and differentiate natural log. But because this is not just a constant times a function, it's the product of two functions, that requires the product rule. So the first factor is x plus 1. What's the derivative of the second?
1 over x minus 2.
1 over x minus 2 times the derivative of the x minus 2, but that's just 1, so I don't have to write it. That's the first factor times the derivative of the second. So I'm ready for the second factor times the derivative of the first. What's the derivative of the first? Just 1, and I don't have to write it. Now, I don't know how much cleaning up there is going to be here. I certainly can multiply both sides by y because I'm solving for y prime just like I have been on all the problems. But generally, the only time that in the back of the book they will have bothered to get a common denominator and add two rational expressions is if they're both algebraic expressions. if you've noticed, I don't think they will have gotten a common denominator and added these because one of them is algebraic and, what's that other word for non-algebraic? Transcendental. It's in the title of your book. Yeah, they don't usually get a common denominator to add algebraic expressions and transcendental expressions. So is there, yes, question?
So we're still solving for y prime?
Always. Because y prime stands for what?
The derivative.
The derivative, and what did the directions say find? The derivative. Yep.
Yes, no. We still are, always? Is that what you said?
I'm trying to understand what your question is.
Oh, you said always.
Yeah, if the directions say find the derivative, then yes, we're solving for y prime. Now we could have different directions. So my always only meant when the directions say find the derivative.
Gotcha.
Okay. So is there anything else I can do or should do?
75, please.
And 33.
Can we finish this one?
Sure.
I know why you said that. I said, is there anything else I can do? I meant to this problem. We wanted the derivative in terms of x, not in terms of x and y. So put this original expression for x back in the place of y. And my gut says that that's how they'll leave it in the back of the book, because if I wanted to, we've already decided not to get a common denominator and add those. We usually want our answer factored as completely as possible, so why would I distribute if I want my answer factored? This already is factored, so I would just leave that as my answer. All right, I only have time to do one more of these before we have to do the new stuff. If we happen to finish the new stuff early, which we never have, then I could do more problems from the homework. So y'all and Harriman are going to have to thumb wrestle and come to a decision. Which one do you most want to see next?
33.
I hear it, 33. What else? I'll tell you which one I think's the hardest. 33 and what else?
75 is pretty bad.
75, 33, and 75.
This is bad getting the common denominator. That's the worst.
The algebra's bad on 75. 75. Yeah, I can see 75 would be tougher algebraically. I can also think of a most common mistake folks make on 33, and I want to address that because I don't want you to make that mistake on the retest. The most illegal thing that you could possibly do.
The retest is next Friday, not this Friday, right?
Correct. Next Friday is the academic festival. We don't have class that day. I may be able to get to that room before 1. If you want to come, at 12:30, you can. But I don't know if there'll still be something going on in that room. I'm not sure it'll be clear until 1. So right. I may get there at 12:30, and if it's clear, y'all can start. If it's not clear, we could find another place to sit and talk and answer some questions if you need it.
This stuff right here won't be on the retest.
No, but this thing I'm fixing to tell you could be. This most common mistake, you wouldn't see an implicit differentiation problem on the retest, but you could have a problem like tangent of 5x plus 2, and folks still make the most common mistake. Miss Ashley, what did you ask me?
Does no one have class on Thursday?
Friday. No day classes next Friday. The academic festival.
Oh, it's Friday. I thought
Correct.
it was Thursday.
No. All right. The most common mistake that you could make on 33 was trying to distribute that tangent. That does not mean tangent times x plus y. It's tangent of x plus y. You can't distribute tangent any more than you can distribute natural log or distribute an exponent. You can't do it. You have to say the derivative of tangent ugly is what?
Secant squared, ugly times.
Secant squared, same old ugly, times the derivative of the ugly. Is that going to take the product rule? No, I don't have a product. What is the derivative of the x? 1. Do I have to write that 1?
Yes.
Yeah, because it's a term. It's not just the coefficient of something. It's a term. And what's the derivative of the second term? Y. Y prime. What's the derivative of the right-hand side? 1. All right, person who asked for 33, did you get that?
Yes.
Okay, and so it was the solving for y prime that bothered you?
Yeah.
Okay, or maybe it was just the way they wrote the answer, because I can think of 2 different things you could do here, and they would give you 2 different looking answers, but the answers would be equivalent. Normally, if I just had, say, a constant times 1 plus y prime, I would distribute the constant. I think here the easier looking answer would result from dividing both sides by secant squared instead of distributing secant squared. Both of those things are legal. One will give us a simpler looking answer than the other. So I'm going to divide by secant square. And what the heck is 1 over secant square? You're close. You're totally wrong.
Cosine squared.
Cosine square. All right. 1 over secant square is cosine square. Look how much simpler the whole thing looks now. So it sounds like you didn't miss the calculus. You probably didn't even miss the algebra. I'm guessing that you left your answer maybe as either 1 over secant squared, or you recognized, hey, that's cosine squared, but then you left it as that. What is cosine squared minus 1? Negative sine squared. Your Pythagorean identity, sine squared plus cosine squared equals 1. If you solved that for cosine squared, if you got a cosine square minus 1 using this, well, if you subtracted cosine square from both sides, you would have 1 minus cosine squared, but that's not what you want. You want cosine squared minus 1, so subtract the 1 and subtract the sine squared. Cosine squared minus 1 is negative sine squared. So was it only how did they get the sine squared that you were actually asking about?
Yeah.
Yes.
It was Pythagorean identity. And one of the very few trig identities that actually, I do expect that to pop in your head. The Pythagorean identities we've used so much that, if you have a 1 and a cosine squared, you can probably write it simpler than that. Or a 1 and a sine squared, a 1 and any trig function squared, you can probably write it more simply.
You can just remember the first one right there.
Oh,